Welcome back to another example video on diagonalization. Our last example, we verified if the given matrix plus its invertible gave us a diagonal matrix. In this video, we will continue doing that. However, we are not given our invertible matrix, so we actually have to find it and then verify that it does give us a diagonal matrix and that the diagonal matrix are the eigenvalues. So let's get started. The first one is going to be, well, both of them are going to be a 2x2 matrices. We're going to do a 3x3 in the future, which will more likely be the next video. So the first 2x2 matrix, we have 6, -3, -2, and 1. Just like any other process, when it comes with these, we always find our eigenvalues and eigenvectors. So to find our eigenvalues, we have to use the characteristic equation. And so you can use either characteristic equation. This is my preferred one. And so now we have 6 minus lambda, 1 minus lambda, then minus 6, and that is equal to 0. We are going to distribute a little bit more. So we have 6 plus lambda squared minus 7 lambda minus 6. The 6's will cancel out. How lovely. And this will we can factor out the lambda as well. So we have lambda times lambda minus 7, that's equal to 0. And that will only be true when lambda is 0 or 7. So now that we have our eigenvalues, we can find our eigenvectors. So the easiest one would be when lambda is equal to 0. And that is because the matrix remains unchanged. And so for that to be equal to 0, our eigenvector will be 1, 2, and then the other one, when lambda is equal to 7, we'll have the matrix -1, -2, -3, 1 minus 7 is -6. And so for that to be true, we'll need a eigenvector to be -3, 1. Now, to find our S, it is simply the eigenvectors in like just column form. So the first one should be 1, 2, and then the next one has to be -3, 1. So now we have to find the inverse and then multiply it all together to show that it gives us a 1 diagonal matrix and 2 eigenvalues along the diagonal. So our inverse of S will just be 1 over 1 times 1, which is 1 minus 2 times -3 is -6, so that'll be +6. And then the matrix, we switch to, no, there's no negative. We switch to the diagonals, and then we flip the signs of the other one. I'm not going to distribute the 1/7 because I don't want to deal with fractions, but we can now use our formula. The d is equal to SAS, this part right here. So 1/7 times 1, -2, 3, 1 multiplied by matrix A, 6, -2, -3, 1 multiplied by our invertible matrix S, 1, 2, -3, 1. And so that will give us the first matrix will remain unchanged, 3, 1. Then when we multiply, we have 6 times -6, so give us 0. And the other one will give you -18 minus 3, -21. Then we have -2 plus 2 be 0. And -2 times -3 is 6. Plus 1 is 7. Simplify this a little bit further. We'll have 1/7. And then we'll have because we have a column of zeros, our columns will be zeros. Or yeah, one column 0 should be that column would just be zeros. And then the other side we have 1 times -21 should be -21 plus 7 times 3, which is 21. That will give us 0. Then lastly we have -1 times -21, which would be 42, plus 7, which would be 49. And then we can finally distribute the 1/7. So we'll have 0, 0, 0, 7. Cool. We just showed that this gave us a diagonal matrix, and our main diagonal has the eigenvalue 0 and 7, which is the one that we found. So now let's do the other one. Other one, again, same thing. Find the characteristic equation, or find the roots of the characteristic equation, and then find the eigenvectors minus lambda. And so that should be 1 minus lambda, 8 minus lambda, then -4, -2 will be 8 minus 8. And that will be equal to 0. So we're going to distribute this once more. We'll have 8 plus lambda, plus lambda squared minus 9 lambda plus, 8. It'll be minus 8. It's equal to 0. 2 cancel out. And we can factor out the lambda. We'll have lambda times lambda minus 9. And that's equal to 0. So we know that lambda is going to be equal to 0. This is going to be equal to 9. So now we have to find our eigenvectors. So the easiest one is when lambda is equal to 0, because the matrix will remain unchanged. And so our eigenvector will just be 1 times something plus -4 times something, make it equal to 0. Now be if 1 is multiplied by 4 and then -4 is multiplied by 1. And that should agree with the second row. So now when lambda is equal to 9, we'll have 1 minus 9 is -8, -2, -4. 8 minus 9 is -1. And so the eigenvector for this one will be, let's keep the 8. So we'll have -8, and then now we have 4 times, -4 times something will be 0. So this will be -2. Now that we finished that, we have our invertible matrix S, which would be 4, 1, then 1, -2. The inverse will be 1 over 4 times -2 is -8 minus 1. Then we switch these two and then flip these. Again, now we have to plug in our equation. I am not going to distribute the -1/9 because of I don't want to deal with fractions. -1/9, then -2, -1, -1/4. You have to keep in mind that you have to keep this in order. So the inverse of S, A, and then S, you cannot flip them because that will not give you the answer. Because if you recall back then, matrix multiplication is not commutative. And so I think I wrote these all right. So this will now equal to D, our diagonal matrix, which will be -1/9. The first one remains unchanged. So we're going to multiply the last two. We will have 4 times 4 minus 4 times 1. No, 1 times 4 minus 4 times 1. That'll be 0. And then we'll have 1 times 1 minus plus 4 times 2 is 8. So that'll be 9. Then the other one we have -2 times 4, which would be 8 plus 8. That'll be 0. Then -2 minus 16 is -18. Then again, now we can multiply these matrices. Then we have a column of zeros. That means the first column is going to be zeros. Now we have -2 times 9, which would be -18, plus -1 times -18, which would be 18. That will give you 0. And then lastly, we'll have -1 times 9, which will be -9. 4 times -18, that'll be 2 for -72 minus 9 be -81. And so now we can distribute the -1/9, and we are left with 0, 0, 0, 9, which is another diagonal matrix with the eigenvalues across the main diagonal. One little observation which is kind of unique is the column in which the eigenvalue is, the diagonal matrix is corresponds to the eigenvector of the invertible matrix. So for the case when lambda is equal to 0, for the part B, we found that our eigenvector is 4, 1. And what you know, the first column on the invertible matrix is 4, 1. Same thing goes with 9. 9, we found that to be 1, negative 2, and that is in the second column. And then diagonal, it's in the second column. Same goes with part A. We have our 7, which is in the second column, which corresponds to negative 3, 1, which is also in the second column of S. And then you can say the same thing with 0, with 0 being 1, 2, and it's being in the first column of S. So that's another way you can verify that your eigenvalues are correct. If the eigenvalues and eigenvectors aren't in the same columns, then everything is correct. If not, then you messed up somewhere. But yeah, that'll pretty much be it for this video. The next video is going to be the same thing as this one. However, is going to be working with the 3x3 matrix. So it's going to be a much longer example. And yeah, I'll see you guys in the next video.